Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to discuss another important topic. The topic is field. Let me explain the idea of field in general. Then we will discuss the particular case of electric field. Right? So, what is field? See, if we talk of temperature in the room, in the room in which I am staying, or in the room in which you are listening, this temperature in the room has a definite value at every point in the room. So it has a definite value at every point in the room. For example, my room or your room, right? So we can measure this temperature at each point by putting a thermometer at that point, and then we could then represent this temperature distribution throughout the room either with a mathematical function like I can write T of x, y, z, where x, y, z or z are the rectangular coordinates of point. That means I have my space in the room. Now I take a rectangular coordinate system. Now at each point P in this space, temperature has a value. So I can express this distribution of temperature at all points in the room with a mathematical function where T represents temperature and it is function of position x, y, z. Right? You can use mathematical expression to express this temperature distribution, or we can use a graph. We could plot temperature as function of position and see how this temperature varies with position in our room. Now, such a distribution of temperature in the space is called a temperature field. So we talk of temperature field. Similarly, we can talk of pressure field. Pressure in the room has definite value at every point in the room. So simply you can express this pressure as function of position. Then you can find some mathematical function which gives dependence of pressure on position, or you could use the graph. So this distribution of pressure over the space in the room we call pressure field, right? So there can be many physical quantities which have different values at different points in space. So we talked about temperature field, we talked about pressure field. There are other fields. There is gravitational field surrounding some mass. There is electric field surrounding some charge. So we talk of such fields in physics. We use this idea in maths as well. Now, in all these examples, if you see, there is a particular region of space And at every point of this region, some physical quantity has a value, whether it is temperature, pressure, electric field, or gravitational field. Now, the term field, let me write it. The term field is used to mean both the region and the value of the physical quantity in the region, right? So we have space. In space, there exists some physical quantity. That physical quantity has definite value at every point in the space. We express that as some mathematical function or graph. We can express that using some graph. Now, the term field is used to mean both the region and the value of the physical quantity in that region. So, when I say temperature field, it means there is some space in which temperature has a definite value at every point. When I say pressure field, it is understood I am talking of some space in which there is pressure, and pressure has definite value at every point in that region, right? So we talk of fields in this way. Now we can have some fields can be scalar. Sometimes we say the field is a scalar field. Sometimes we talk of a vector field, right? It is understood if the physical quantity in question is a scalar, then the field is a scalar field. If the physical quantity in question is a vector, then the field is a vector field, right? So temperature is a scalar quantity, so it is a scalar field, right? Pressure is a scalar field, right? But when we talk of gravitational field, that comes in the category of vector field, right? So we can have a scalar field, we can have a vector field. Similarly, we use terms like static field. Now, what are static fields? Those fields which doesn't change with time. That means they are constant in time. And we talk of time varying fields. Time varying fields is understood those fields which vary in time. That means if the values of the physical quantity in the space change with time, then the field is time varying, and if the values of the physical quantity in question in the space, concerned space, doesn't change with time, then the field is a static field. So you can have a scalar field which is static. You can have a scalar field which is time varying. You can have a vector field which is a static field. You can have a vector field which is a time varying field, right? Now, in reference to gravitational field, let us talk about now first gravitational field. This was the general introduction to the idea of field. Let me talk about the idea of a gravitational field. Now we know everything else attracts everything else. Due to gravity, everything else attracts everything else. Everything else attracts everything else due to gravity. You know it. Now, when we talk of this gravitational force, we know we have some masses. For example, if I have mass m1 and m2, we know there is gravitational force between them if they are separated by distance r. Then the magnitude of the gravitational force between these 2 point masses is given by Newton's law of universal gravitation. F is g m1 m2 by r square, where g is gravitational constant. Now, this interaction between two masses is explained. We have two notions of understanding this interaction, or I can say there are 2 point of views, two points of view with regard to the interaction between two masses. First point of view is called the action at a distance. Action at a distance. By that, what we mean? In action at a distance point of view, we say the interaction between these two masses m1 and m2 is direct and instantaneous. So, in this point of view, interaction is direct and instantaneous. Instantaneous. By direct, we mean there is no third party, no intermediary agency between m1 and m2 with regard to the interaction between them. So we symbolically write this action at a distance this way. We write mass, then show this double arrow and write another mass. So this is how we depict the action at a distance. So there is no intermediary agency between mass m1 and m2. One mass exerts force on other mass, and in return that mass exerts the force on first mass. There is no third party or intermediary agency with regard to the interaction between these two masses. That's the meaning of direct. What about instantaneous? See, from this Newton's law of universal gravitation, you can see if you fix the masses, you take some masses, now fix their mass. Now, if you change the distance between them, what will happen? The force will change. If r is increased, force will decrease, and if r is decreased, force will increase, because F is inversely proportional with r square. Now, question is, when I move m1 relative to m2 or m2 relative to m1, now other mass will sense the moment of one mass. Now, when it will sense that is the question. Now, in this action at a distance idea, we say the moment I move m1, m2 senses at that particular instant its movement. How it senses? It senses in terms of the change in the force between m1 and m2. So in this action at a distance idea, we say interaction is instantaneous. That means irrespective of the distance between m1 and m2, when you move m1, m2 senses its movement instantaneously. When you move M2, M1 senses its movement instantaneously. How? There will be change in the force. There will be change in the pull, right? Irrespective of the distance between M1 and M2. Whether the distance between M1 and M2 is 10 light years, 20 light years, any distance, when you move M1, M2 senses its movement at that particular time, right? That in a way means, in a way or not in a way, that means when you move M1, the signal, this message from M1 reaches M2 instantaneously, irrespective of the distance between M1 and M2. If you move one mass, the message goes to and the mass that it has been moved, and that message takes zero time. Because we say M1 is moved, M2 senses at that particular moment there is no time interval between the instant one mass is moved and the instant other mass senses that movement. So we are saying in a way that the signal from one mass to other mass takes zero time to reach, to arrive. Therefore, its speed of the signal is infinite. Because if I say, for example, if there is some wall and I have a ball, some ball, and there is some distance between ball and wall, for example, some x meters are there. Now, if I throw this ball towards the wall and I say this ball hits this wall instantaneously, that means the instant when this ball leaves this point P and the instant this ball hits this point Q is the same instant. There is no time interval between those two instants. That, in other words, means that ball takes zero time to travel x meters. So you know speed is equal to distance by time. So if this distance is covered in zero time, speed becomes infinite. So that means speed is infinite. So when I say this ball hits this wall instantaneously, that means ball moves to wall at an infinite speed, which is meaningless, right? And similarly, when I say the interaction between M1 and M2 is instantaneous, we are saying that the signal moves from M1 to M2 at in zero time, it moves at infinite speed. But we have a speed limit in physics. Remember, we have a postulate of spatial theory of relativity, postulate of spatial theory of relativity. This postulate of spatial theory of relativity, there are two postulates. I'm talking of one postulate. This postulate says that the speed of light, the speed of light in vacuum, which is denoted by c, which is approximately 3 into 10 raised to 8 meter per second. The speed of light in vacuum c, 3 into 10 raised to 8 meter per second, is the speed limit of our universe, speed limit of our universe is the speed limit of our universe. What does that mean? That means no particle or no signal can exceed this speed. Is the limiting speed. It has been established in laboratories also. When we try to speed up elementary particles, their speed saturates and this c becomes their limiting speed, right? So they approach to this speed, but they never touch this speed. They never reach this speed. So this is the speed limit of this universe. So when I say the interaction between the masses is instantaneous, I am violating this postulate of special theory of relativity, because I am saying this signal from M1 to M2 goes instantaneously, it takes no time, though, so speed is infinite. So that's why we discard this idea. So the point of view with regard to the interaction between two masses, which uses the idea of action at a distance, this point of view is discarded because of this issue, that it violates the speed of limit principle or postulate set by the special theory of relativity and established through various experiments done in different laboratories throughout the world. So we therefore introduce the field idea. In field idea, what we say interaction is neither direct, interaction is neither direct nor instantaneous. And we symbolically represent it this way. We write mass, then we show double arrow, in between we write field, then double arrow, and we write this mass. So now in this field idea, we say that field is the third party in this interaction. It is the intermediary agency. In action at a distance idea, we say this mass directly exerts force on another mass. This is M1, M2, there is no intermediary agency. Now in field idea, what we say this mass M1 has a field surrounding it. There's a field in space surrounding this mass M1. And if in that field M2 finds itself, that field exerts force on M. See the difference? In action at a distance idea, we say there is a field, there is no idea of field there. We say M1 directly exerts force on M2. But in the field idea, we say there is a field surrounding M1, and if M2 finds itself in that field exerts force on M2, not M1. Similarly, M2 will have its own field surrounding it. Now, if M1 finds itself in the field of M2, the field of M2 will exert force on M. So there is a third party. That third party is field. So interaction is not direct. Now, what about this? It is not instantaneous also. That means if you move M1, what will happen? There will be change, disturbance in the field of M1, and that disturbance will reach M2 at the speed of light c, not instantaneously. Therefore, what will happen if, for example, according to the field idea, if the distance between M1 and M2 is 3 into 10 raised by 8 meter per 8 meter, if you move M1, M2 will sense that movement after 1 second, because the speed of light is 3 into 10 raised by 8 meter per second. That means light travels this much meters in 1 second, and we are saying when M1 is moved, there is disturbance in its field, and that disturbance reaches M2 at speed c. So if there is 3 into 10 raised by 8 meter distance between M1 and M2, if you move M1 after 1 second, M2 will sense that movement. The signal doesn't go instantaneously from M1 to M2. So it is in compliance with the speed limit set by the postulate of spatial theory of relativity. Similarly, for example, there is the distance between m1 and m2 is 1 light year. Remember, 1 light year is the distance traveled by light in 1 year. So, if the distance between m1 and m2 is 1 light year, if you move m1, action at a distance says m2 will sense at that same moment when you move m1. But field idea says that when you move m1 after 1 year, m2 will sense its movement because distance is 1 light year. Light will take 1 year to travel this much distance, and we know the disturbance in the field of m1 will travel at the same speed. So after 1 year, m2 will sense movement of m1. So this field idea was introduced to make theory gel with the speed limit set by the spatial theory of relativity and which has been experimentally established. Same goes with the electric field idea. Now you can extend this action at a distance idea and field idea to electric field as well. Only you have to replace masses by charges. So if we talk of action at a distance idea with regard to electric field, then we symbolically write it this way: charge, double arrow charge. And idea is same. There we say the interaction is direct and instantaneous. That means there is no third party. Charge 1 exerts force directly on other charge, and there is interaction is instantaneous. If you move one charge, second charge senses its movement instantaneously irrespective of the distance between the charges. But in field idea, we write it this way: charge, field, and charge. Right? So there we say interaction is neither direct nor instantaneous. Field is the intermediary agency. So if I have some charge Q1, it will have its own field, right? And if in that field Q2 finds itself, that field will exert force on Q1. Similarly, Q2 will have its own field. If Q1 finds itself in that field will exert force on Q1. So field is the intermediary agency. Interaction is not direct. It is not instantaneous. Again, if Q1 is moved, there is a disturbance created in its field and that reaches Q2 at speed of light c, not instantaneously. That means, again, if there are two charges Q1 and Q2 at 1 light year distance from each other, if you move Q1 after 1 year, Q2 will sense its movement. So this field idea was introduced in this way, right? So I hope it is clear to you. So we talk of fields, we can have a scalar field, we can have a vector field. And what is a field? We have some space. In that space, there is some physical quantity. That physical quantity has a definite value at every point in the space. Now, the term field is used to mean both the region and the value of the physical quantity in that region. Then we said we can have a scalar field, vector field, time varying field, static field, and we talked about the gravitational field, why we use the idea of field in gravitation or the idea of field in the case of electric interaction between charges. Because to make theory gel with spatial theory of relativity, because these restrictions imposed by spatial theory of relativity postulate have been experimentally verified. This was about the field. Now I'll show you a numerical a simple problem before stopping my lecture. So let us move to the question. One simple problem we will do. Question is this: what is the magnitude and direction of the force on a charge of plus 4 into 10 raised power minus 9 coulomb, that is 5 centimeter from a charge of plus 5 into 10 raised power minus 8 coulomb. This is a simple problem. Let us do it. So, question says what is the magnitude and direction of the force on a charge of plus 4 into 10 raised power minus 9 coulomb, that is 5 centimeter from a charge of plus 5 into 10 raised power minus 8 coulomb. So we have two charges, Q1 and Q2, and the distance between them is R, which is 5 centimeter. So one charge is plus 5 into 10 raised power minus 8 coulomb. Second charge is plus 4 into 10 raised power minus 9 coulomb. Plus 4 into 10 raised power minus 9 coulomb. Second is, so both charges are like, so there will be repulsive force. That means the direction of force on Q1 will be directed away from Q2 this way. We name it F12, force on 1 due to 2, and same force will act on Q2 but in opposite direction, F21, right? Force on Q2 due to Q1 will have same magnitude. This is an axial reaction pair directed away because there is a repulsion. Both charges are like. What about their magnitudes? The magnitude of F12 is same as the magnitude of F21, and both are equal to K Q1 Q2 over R square. Let's put the numbers. K is 9 into 10 raised by 9 Newton meter square per coulomb square in SI system. And you have Q1, which is we're talking of magnitude, so we don't need to write here plus. It's just 5 into 10 raised by minus 8 coulombs. Then you have Q2, 4 into 10 raised by minus 9 coulomb. Then you have distance. Distance is in centimeters, so we convert it. So it is 5 into 10 raised by minus 2 meter. 1 centimeter is 10 raised by minus 2 meter. So let me put it here. 5 into 10 raised power minus 2 meter whole square. So K, Q1, Q2 over R square, 5 into 10 raised to minus 2 meter whole square. When I do this calculation, it turns out to be 7.2 into 10 raised to minus 4 Newton. This is the magnitude of the force You need to check this calculation at home. Check this calculation at home. So the magnitude of the force is 7.2 into 10 raised to minus 4 Newton. So the answer to the question is the force is directed away from plus 5 into 10 raised to minus 8 coulomb charge, and that force has this much magnitude, 7.2 into 10 raised to minus 4 Newton, because both charges are positive, like charges. There is repulsion. So this is all for today. Don't forget to like, share, and subscribe my channel. You can give comment in the comment box. Thank you. God bless you. Assalamu alaikum.